Good evening to all of you. In today's lecture, we will discuss the design of footings. So, what do you mean by footing? First, footings are a structure members used to support columns. So, footings are used to support the columns as well as walls, like shear walls, and to transmit and distribute their loads to the soil. Okay, but the condition is that the bearing capacity of the soil is not exceeded. Bearing capacity means load supporting power of the soil is not exceeded. That is, the footing does not settle into the ground. And second point is excessive settlement, differential settlement, and rotation of the footing are prevented and adequate safety against overturning or sliding is maintained. So basically we have two functions. The first one is that it is used to support the load of the columns and walls, okay, and they transmit their load to the soil in such a way that number one, bearing capacity is not exceeded, number two, settlement, differential settlement, okay, are prevented, and at the same time it should also provide adequate safety against sliding or overturning. Now basically there are types of footings, two types. One is called shallow foundation and second is called deep foundation. So as the name suggests, shallow means which have small depth foundations. They are called shallow depth. Okay. And we have deep foundation, whose the depth is very large. Okay. So we will discuss both these types. What is the meaning of shallow foundation? What is the meaning of deep foundation? Now the choice of this foundation, that is whether you choose shallow or deep, will depend upon these factors. Number one, depth at which bearing strata lies. Means the hard strata below the top surface of the soil or the ground. Okay. Suppose that if the hard surface is available at a depth of suppose at 2 meter from the ground level, then that is called the depth at which bearing is present. It is called bearing strata. Okay. So if the hard soil is available at a depth of 2 meter below the ground surface, then we have to rest our foundation at that level. Second is what will be the soil condition. If the soil is loose, we have to provide different types of foundation. If it is hard, we have to provide a different type of foundation. If it is a, can say that the uh, if the soil is suppose that marshy type, okay, then in that case we have to provide a different type of foundation. And the third one is type of superstructure. What is the superstructure? Means what is the type of the building? If it is a very high-rise building, like suppose at 50-story or 100-story, we have to provide different type of foundation. If it is a bridge structure, then we have to provide a different type of foundation. If it is a normal 2 or 3-story structure, then we have to provide different types of foundation. So these three factors are solely responsible for the choice of foundations. Apart from this, one more factor is that is magnitude and the type of reaction at the base of the superstructure. Type of reaction means how much load will come to the foundation from the superstructure. That is also decide the type of foundation. Now come to the shallow foundation. Shallow foundation are used when the soil has sufficient strength within a short depth. Suppose that if the soil near the ground surface is sufficiently hard to take the load of the superstructure, then you have to provide the shallow foundation. Okay. Now for shallow foundation, dF by B ratio. dF means depth of foundation divided by the width of the foundation. Is ranges between 0.25 to 1. Okay. If the ratio is up to 1, that is D by B is up to 1, then we call it as shallow foundation. Okay. Now these are the various types of shallow foundations. Like suppose that we have this wall here. For this wall, we have this footing here like this. So this is a isolated footing that is called your wall footing. Second one, we have a column here and we have a foundation for this column. Okay. So we call this as in the plan, you will see that this is my column and this is my foundation. This is called your spread footing. Okay. C, it is called stepped footing because we have a step here. One step here, second step is here. Okay. So the top one is called your pedestal or the step. Okay, this one. Pedestal, this is my column, this is pedestal, this is your foundation. So this is called your stepped footing. And we have sloped footing. So we have the column here, we have the platform here, horizontal platform, we have a base here, and we have provided this sloping surface. Generally, in 4 to 5 story building, we have to provide this type of foundation that is called sloped foundation. Okay, so all these are called your shallow foundations. Then we have combined footing. Now, when the spacing of the adjacent column is close, suppose that the two columns which are close in a building, so what will happen? The isolated footing areas will merge into each other. Okay. So in that case, it is not possible to provide separate isolated footings because the areas of the footing are overlapping each other. So under such condition, what we'll do? We have to provide a combined footing. Okay. So that combined footing, the shape of the combined footing may be rectangular or may be trapezoidal. Okay. With or without a beam joining the two columns. I will show you how it is provided now. Such columns footings are used when one column is near the property line. Now the property of this combined footing is that the first condition is that when the areas of two uh, uh, column footing areas are overlapping each other. This is the first condition. And most of the time when a column is situated near the property line, then in that case you have to provide the combined. Like suppose that, look here, this is my one column is this one, this is another column. Okay, if I provide separate footing for this one and separate footing for this one, what will happen? The areas of this footing will overlap each other. So in that case, I have to provide one combined footing. Okay, so this means that two footings close to each other. So in that case, I have to provide a combined. This is my column, and this is your combined. Clear? Now, second case, suppose that if my one column is close to property line, suppose that this is property line, another property is there. Okay, so I cannot go my foundation in the other property. So what I will do, I have to use my own area. Okay, so in that case, what I will do, I will connect this column and this column with one footing here. Okay, so this is the condition when we generally encounter in case of property line, columns near to the property line. So here P1 is close to property line. This P1 column is close to property line and P2 is greater than P1. Now the load on this column, on the column which is inside to this P1 is more than this P1 here. Okay, so in that case we have to provide this rectangular combined footing, okay, of this type. Now suppose that, come to the third condition. Again, this is my property line here. Okay, but the ratio of P2 by P1 is between 0.5 to 1. Then in that case, we have to use trapezoidal footing with more width of the trapezoid near the property line here. Okay. Now suppose that if P2 by P1 is less than 1 by 2, okay, this is my P2, this is my P1. If P2 by P1 is less than 1 by 2, then in that case, I have to use a strap compound. Strap means this is one footing here, and I connect both the footing with the help of a beam. Okay, at the footing level. So this is my beam. So this is called your strap. Okay, so such type of footing is called strap combined footing. So these are the possible cases of the combined footing. Now, how to provide reinforcement in combined footing? Now, this is my one column here. This is my another column here. Okay. So if you see in the cross section, this is load P1 here. This is load P2 here. Now, under this load, the deflection of the footing will be in this direction. It is deflected down. So we have to provide steel here. Okay. Steel in this direction and steel in the perpendicular direction. Similarly, we have provided steel here. Okay, but between this column and this column, we have a hogging moment here. You see the diagram here. This is my sagging moment, and this is my hogging moment from here to here, between this column and this column. Because of this hogging moment, what I will do, I have to provide a steel at the top level. Okay, so this is the provision of the steel in case of combined. Okay, apart from the steel under the column, I have to provide a steel between the two columns at the top level of the footing. Now, what is the strap footing? These are the strap footings. This is one column here, one column footing here, one column footing here. I have to provide a beam like this. We have a deeper beam that is called your strap beam. Similarly, here in this case, this is my one column near the property line. This is my another column, okay, which is inside. So this is one footing, isolated footing. This is one isolated footing, but the distance between these two footings is more than 2.5. Okay, then in that case, I have to provide a beam here, which is called your strap footing. The strap beam will not transfer any load to the soil. Now, this beam will not transfer any load to the soil. The load is transferred only through the column and the footing. Now, what is raft foundation? These are special cases of combined footing where all the columns of the building are having a common foundation. If suppose that these are my column 1, 2, 3, 4, 5, and we have several rows of the columns, or all these columns are provided on one footing, one large footing. Okay, so that one footing is called your raft foundation, where all the columns of the building having a common foundation. Okay, now where it is used? It is used for building with heavy loads or when the soil condition is poor. The soil condition here is not good. So raft foundation is very much useful to control the differential settlement. Now this is a threshold situation for shallow footing beyond which deep foundation have to provide. So this is the last step where you can provide the shallow foundation. After this condition, you should always go for the deep foundation. So deep foundation means pile foundation. Okay. So piles are very useful in marshy land. Marshy land where we have very loose soil over the top. Always the land is submerged in water for a very long period of time. Okay. We call it as daldal, marshy land where other types of foundation are impossible to construct. Okay. So in that case, we have to provide a deep foundation like this. These are the piles. Okay. These are the piles. Now such foundation DF by B ratio is ranged between 5 to 20. For shallow foundation, this ratio is 0.25 to 1. For deep foundation, this is 5 to 20. So such type of footing are required for very tall buildings like 50-story or 100-story, or in case of bridges also. Okay, where the foundation is continuously under the river water. Okay. Now, how to calculate the depth of the foundation? So we have a formula which is called Rankine's formula, which gives the minimum depth of the foundation by this. Okay. So DF means depth of foundation. This is the formula. QA by gamma is 1 minus psi phi 1 plus sin phi whole square. What is this? DF means minimum depth of foundation. Okay. QA means safe bearing capacity of soil. This is my bearing capacity. Gamma is the density of the soil. Okay. Phi is angle of repose of soil. It is also given in the problem. Angle of repose. Now, what is the design considerations? First is your minimum nominal cover. How much cover you have to provide? Now, in case of foundation, maximum cover is provided if you compare with all the structural members. Like in case of slab, we provide 20. In case of beam, we provide 25. In case of column, we provide 40. But in case of foundation, the minimum is 50 millimeter. Okay. Now, what is the thickness at the edge of the footing? Now, generally, we provide slope foundation. So, at the edge, we have to provide a minimum thickness of 150 millimeter at the edge. Okay. If the footing is on the soil, means for shallow foundation, you have to provide 150 millimeter. And at least 300 millimeter above the top of piles if the footing is on piles. If suppose that we provide the fault foundation, pile foundation, then you have to provide minimum footing as on the minimum thickness at the edge is 300. Now, next criteria for design is bending moment. Okay. So, bending moment at any section shall be determined taking all forces acting over the entire area or one side of the section of the foot. I will show you in the next slide how to calculate this bending moment. This is as per clause 34.2.3.1. Okay. Now, come to the critical section. Now, look here. If you want to calculate the bending moment, okay, this is my column here, okay, and this is my footing. Clear? Now, for calculating the bending moment, you have to consider the section 1, which is passing just adjacent to the column here. This is my 1. So this is my critical section for bending. You have to calculate the bending moment at this section. Okay. Similarly, one face of the column is this one. So this is my section for bending. So here critical section for moments is 1, 1 and 2, 2. Clear? Now the critical section for bending moment for the purpose of designing an isolated concrete footing which supports a column shall be at the face of the column. So critical section for bending moment will be at the face of the column here as well as here. Okay. Now one more thing. Here this is a section 3.3, which is nothing but your critical section for one-way shear, which is at a distance of small d from the face of the column. So this is for one-way shear. It is at section is 3.3 and 4.4. So this is my 3.3 here, and this is my 4.4. Again, this is at a distance of d for one-way shear. Okay. Similarly, we have two-way shear. For two-way shear, we have to consider an area around the column here. This is my area. Okay, indicated by 5, 5, 5, 5. This is at a distance from here. This is d by 2. This is d by 2. D by 2 here, d by 2 here. Everywhere d by 2. Okay, so this is the critical section for two-way shear. Basically, there are two types of shear. One is one-way shear, which is at a distance of small d from the face of the curve, and one shear is two-way shear, which is at a distance of d by 2 everywhere. Okay, d by 2 everywhere. So this is my one-way shear and two-way shear. So look here again. I will see this is my column here. C1 side here, C1 side here. This is my footing side, B here and B here. Okay. So critical section for bending moment will be passing from the edge of the column here. Okay. So this is the critical section for bending. Similarly, one more section for critical section for bending here. If the column is your rectangular, if it is square, there is no difference. Just consider one column here, one section. Okay. Now critical section for shear, that is one-way shear, at a distance of small d, as I explained it to you in the previous slide. This is at a small d here. Okay. So this is nothing but effective depth of the footing slab in case of footing on the soil. And one more thing, so how to calculate one-way shear? You have to use this formula. QU, bearing capacity of the soil. B is the width of the footing here. Okay, for a square column, this is B and this is also B. B minus C1 by 2. C1 is the side of the square column. C1, C1. Okay, minus D is the effective depth of the footing. Okay, so this is small d. So this is the formula for calculating the ultimate shear force at this section. Okay, at a distance of small d. Clear? Where this Q is the upward soil pressure, tau C is the design shear strength. Okay, and you know that VU shear strength of concrete is given by tau CBD. Okay, so tau C is obtained from IS code. The design shear strength of concrete without shear reinforcement is given in table 19 of IS 456. So this value you have to take from IS 456 table number 19. B and D is given here. B is this one and D is this one. So using this formula, you have to calculate the one-way shear. Now, two-way shear. Okay. Now two-way shear, you have to consider two-way shear. This is the dotted line. This is the critical section for two-way shear. Critical perimeter for punching or two-way shear. It is also called punching. Okay. Now, how to take this section, this dotted line? D by 2 here, D by 2 here, D by 2 here, D by 2 here. Okay. So this total distance from here to here, how much? C1 is here. This one. This is C1 plus D. Similarly, in this direction also C1 plus D. Okay. So critical perimeter will be how much? 4 times C1 plus D, because this is your square. So 4 times C1 plus D. So punching shear force will be calculated by this formula. Q, okay, upward soil pressure. B is the side of the footing. C1 is the side of the column, and D is the effective depth of the foot. Okay. So this is your punching shear resistance calculated with the help of this clause. Now Vn2 is given by Ks tau C B naught B. What is this? I will tell you. Ks, formula for Ks is equal to 0.5 plus beta C. Now this value of Ks should be less than or equal to 1.0. Clear? And tau C is given by the code as 0.25 under root of FCK. FCK is the grade of concrete. Now for a square column, beta C is always 1. Beta C is always 1. This one is always 1. And Ks is equal to 1, because the criteria is given as this total value, that is your Ks, should be less than or equal to 1. So for a square column, in any case, this should not be more than 1.0. So Ks is equal to 1. And B naught is the critical shear parameter, that is 4 times C1 plus. This is my critical shear parameter, 4 times C1 plus D. And Vn2 should be greater than Vu2. What Vn2 you are calculating here, this should be more than Vu2 for the footing to be safe in two-way shear. Clear? Normally the thickness of the base slab is governed by shear. So in case of footing, generally we have calculated the depth of the beam or the slab based on the bending criteria. But in case of footing, the responsible criteria or deciding criteria is the shear, not the bending. So normally the thickness of the base slab is governed by shear. Next is your bond. Okay. Critical section for checking the development length in a footing shall be the same plane as those of bending. If you want to find, if you check or do the development length check, okay, in the footing, so it is checked on the same plane as that of bending moment. Bending moment that at the face of the column. Okay. Come to the tensile reinforcement. How much reinforcement you have to provide? Okay. So in two-way reinforced square footing, for square footing, the reinforcement extending in each direction shall be distributed uniformly across the full width oblique length of the foot. So in full width and length, you have to provide a cage for the reinforcement. And the reinforcement criteria are same as that of the slab criteria. That is, minimum is how much? 0.12% of cross-sectional area. That is the minimum scale. Now, taking moment at the face of the column, we get for this criteria, you got this mu is equal to Qu B by 2, B minus C1 by 2 whole square. So finally, you will get this equation. Okay, Qu again, upward soil pressure, B is the width of the footing, C is the side of the column. So using this relation, you have to calculate the moment. Now come to the transfer of load at the base of the column. What you will do? Finally, you have to transfer the load to the base as per this clause of IS 456. So for that, permissible bearing stresses on full area of concrete shall be taken as given below. How will you take it? Bearing stress you are taking as 0.45 FCK. FCK is the grade of concrete. Okay. Accordingly, the permissible bearing stress of concrete in footing is given by this clause. Okay. So for that, we are taking as sigma BR is equal to 0.45 FCK under root A1 by A2. And this whole value, that is the bearing stress means when this is my column here, this is my column here, and this is my footing. Okay. So the bearing stress of this footing should be more than the bearing stress of the column. In that condition, the column will not punch inside the footing, and the footing will be safe. So the bearing stress you have to calculate by this form, and it should be less than or equal to 0.9 times of FCK. Now what is this? With the condition that A1 by A2 should be less than or equal to 2.0. Clear? Now what is A1 and what is A2? I will discuss now. A1 is the maximum supporting area of footing. A1 is this one, maximum supporting area of the footing. Clear? From here to here. Of the footing for bearing which is geometrically similar to and concentric with the loaded area. Now suppose that if this my column is rectangular, okay, so you have to provide a rectangular footing here. If my column is a square, you have to provide a square footing here. So that area, that is A1 area, should be geometrically similar to the area of the column. Clear? This is the meaning. And A2 is how much? Loaded area at the base of the column. This is my A2, loaded area A2 of the column. So A2 is nothing but the area of the column, and A1 is nothing but the area of the footing, this one. Clear? When you do this one, A1 by A2 here, we have to multiply 0.45 FCK. So this is my bearing stress, which should always be less than or equal to 0.9 times of FCK. Okay. Now come to the one more thing, that is if the permissible bearing stress, okay, on concrete in the column or in footing is exceeded. Sometimes what will happen, the bearing stress on concrete here, which I just told you in the last slide, is exceeded. Okay, permissible bearing stress on concrete in the column or footing is exceeded. So what will happen? We have a failure. So in that case, I have to provide a reinforcement shall be provided for developing the excess force. For that excess force, I have to provide some extra reinforcement as per clause this one, either by extending the longitudinal bars of the columns into the footing or by providing dowels. So in that case, I have to provide these dowel bars. Okay, these are my dowel bars. We have to provide some extra steel here, okay, which are called your dowel bars, which are extending into the footing. Clear? So minimum area of extended longitudinal bars. So how much the area of steel is provided for this dowel bar? That is equal to 0.5% of the cross-sectional area of the column. How much steel for column is that here? You have to provide 0.5% for these dowel bars. Suppose that your area of steel for the column comes out to be suppose at 2%. Then you have to provide 1% for these dowel bars. Clear? Of the supported column. A minimum of 4 bars shall be provided. You have to provide minimum 4 bars. One here, one here. We have 4 faces on the of the column, so we have to provide 1 bar at each face. Okay, 1 bar here, 1 bar here, and 2 bars on the opposite side of the column. The diameter of the dowel shall not exceed the diameter of the column bars by more than 3 meters. But care should be taken, the diameter of these bars should not be more than the diameter of column bars by more than 3 millimeters. Okay. Now, in the last, for this clause, our ISO is stipulated that the minimum reinforcement and spacing of the bars in slab, footing slab, as per the requirement of solid slab. So whatever the criteria for the minimum reinforcement for the slab, okay, like one-way slab and two-way slab, minimum requirement is 0.12% of cross-sectional area, and as well as the spacing of the bars. So spacing of the bars and the reinforcement criteria of the slab is also applicable here for the footing. Okay, so in case of footing, we have to provide the minimum area of steel as 0.12% of the cross-section area. Okay, we have to provide same spacing of bars. Spacing means maximum spacing should not be more than 300 millimeter in any case in each direction. Okay, so this whatever the requirement for the solid slab, we have to provide the same requirement uh, for the uh, footing also. Okay, so this is all about the theory of the footings. Next time we shall discuss the design of footing, square footing. Okay, thank you.